So I've heard about phase change. What exactly is it?
Well, the word phase change is describing when something changes state or changes phase. An example of phase changing is ice. When you put ice in a glass of Coke, it melts and it changes phase from a solid to liquid. It's quite simple. In the same way, when you boil water and it hits 100 degrees Celsius, it phase changes into a gas, the water vapour. So phase changing is not complicated, it's not unusual, it's just nature at work. So phase change materials are designed to help stabilise the temperature of a building. If you don't have mass inside a building when you build it, much thermal mass that is, then you end up with a building that swings around in temperature quite a lot. What phase change material does is it actually helps harness the heat of the day and carry that warmth into the night, and helps harness the coolth of the night and carry that into the day, and therefore reduce your heating and cooling loads. So I'm going to show you a few different phase change materials that we have available. This one here is called M91Q23. That means that it can hold 91 BTUs of energy per square foot. It's an American measurement because it's made in North Carolina, this product. But if you translate that into metric, that works out to be around about 280 watt hours per square metre of material. And what that means is, if we put this material inside a ceiling space of a building and we put an electric heater on inside that room, if you had, say, 20 square metres of this material, and it's about 300 watt hours per square metre, that's going to need about 6 kilowatt hours of heat to actually heat it and melt it, and to fill it up with energy. So the long and the short of it is, the more phase change material you put in the building, the longer it takes to get the building up to temperature, and the longer it takes to get it down to temperature again. So different types of phase change material to give you different kinds of outcomes. That one's an M91, it's quite thick and heavy, as you can see. It's quite thick. And it's also got 3 pods all joined together. We also have a different material here, which has got smaller pods. This one here is an M23, M51Q23, and that means that its weight is less, 51 BTUs per square foot, or around about 160 watt hours per square metre. All the details are on the website with regard to the specific information. The 23 number means the point at which the material is full of energy. Now, a traditional thermal mass like brick or concrete, let me find a traditional thermal mass here. This is timber. That's a thermal mass. So if you heat that up, it gets hot. If you put it outside, it gets cold. It has a linear relationship with heat. You put heat in, it stores it. You put it outside, it releases it. It doesn't have any smart temperature range that it operates again through. With phase change material, it's very different. Just like ice. If you take a block of ice that's out of a freezer that's minus 10 degrees and you put it outside, that block of ice will quickly get to 0 because it's a solid just getting warm, in the same way that piece of wood is a solid just getting warm. It doesn't take much energy to heat it up. But once it gets to the phase change point, which is converting from 0 to 1, which is ice to water, that takes a huge amount of energy. In fact, it takes 80 times more energy to melt ice from 0 to 1 than it does to get it from 1 to 2. So, for example, if you put energy into a block of ice and it melts to 1 degree, that same amount of energy, if you put it into water at 1 degree, it'll get to 80 degrees. Just to give you an idea of how much energy is stored in that phase changing process. So what we've got here effectively is room temperature ice. This ice melts, it starts melting at 18 degrees and finishes melting at 23 degrees. So by putting that in the ceiling, we effectively melt the material in the ceiling and then we refreeze it to release the heat again. So you have a look at some pictures behind me here. You can see the material installed inside a building. It's just stapled up inside the voids and the cavities. This was a domed cathedral type ceiling that the customer decided to do. It's not covering all areas, as you'll see, because it's not insulation, it's mass. It doesn't need to cover all areas. Here we've got it just draped between some timber before the plasterboard's installed, and here we've got it inside a wall, just stapled between the studs. The standard sheet sizing is 430 millimeters, so it just gets stapled in between the battens like that. This has the effect of simulating a concrete slab ceiling. Now, if you talk to any energy rating person or any good architect, they'll tell you that lots of thermal mass in a building is good, provided you've got lots of glass to actually gain heat through the winter, and the ability to open the windows at night to release the heat during summer. There's two kind of thought processes. One of them is a really tight building with small windows and lots of insulation and little thermal mass. It's not very nice to live in a building like that because you've got small windows to look out of. Or you can go with a high thermal mass building with lots of nice big windows facing the right direction. We think that's much nicer to live in. The issue is when you build a high thermal mass building, you have to use either Hebel or blockwork or concrete or brick, and as soon as you put weight up really high in a building, you've got to carry that weight all the way through to the ground. So you've got to put a lot of infrastructure in place like steel and other blockwork and concrete to carry all that weight. The other issue with traditional thermal mass like brick or concrete is that it's a dumb thermal mass. It doesn't care what temperature it is. Just like a double brick house in the middle of summer, day 1 it's really nice, day 2 it's not too bad, day 3 it's awful, because the brick keeps on absorbing heat. It's like a Labrador. You give it a bit of food and you give it some more food, it just keeps eating. So a brick wall is just like that. You keep putting heat in, it keeps getting hotter and hotter and hotter until the point you can't even touch it anymore. The difference between phase change and brick for the same thermal storage value is that phase change only works up to the melt point. Beyond that it doesn't have any real thermal inertia, and below its freeze point it doesn't have any thermal inertia. Let's give you an example. If we take this M23 material, sorry, the Q23, 23 degree material, and we put it in a building, and the building is 0 degrees Celsius on a really cold day in spring. Okay, someone left the windows open overnight, and the forecast is it's going to be 30. So you get home and you realise someone's left all the windows open all night, you close the windows, the sun starts pouring in through the glass, the building starts to generate a lot of heat because of the glass. Just like a car in the middle of winter in the car park, it gets hot inside even though it's cold outside. That heat bellows up and hits the ceiling. The ceiling reacts and starts to absorb heat. This phase change material starts to store energy and eventually it melts into a gel. Kind of like this one here is already melted, so it's already soft. Okay, it's full of energy now. Now the house gets up to 23 degrees, this material is full, and you say, well, the house is warm enough, so I won't leave my curtains open anymore, I'll close them. So you close the curtains, and then the house is storing energy at 23 degrees. Into the night it goes down to 0 degrees again. You've got the curtains closed, you've got insulation in your walls, insulation in your ceiling. Then the building slowly releases that heat through leaking through doors and under doors and through windows and things like that. So by the time it gets to morning, the house might be, say, 20 degrees because it released all of that heat again. So then you repeat the process. Is today going to be a hot day? Yeah, it is. Okay, well, really hot, then I'll probably keep the curtains closed because I don't want to store more heat. In that case, the system starts to work as an air conditioner because some of the heat gets through the doors again. Let's say it's going to be 40 degrees today. The material starts to absorb heat and starts to melt, keeping you cool. You probably can't feel this, but I can. If I put that on my face, it actually starts to feel really cool because it's absorbing the heat out of my body. So in summertime, it absorbs heat. At night time, you open the windows and release the heat. In spring, you just manage your curtains and windows to night purge and day collect. In winter time, you typically just leave your curtains open to draw a lot of heat in through the day. So all through the year, phase change material works to help moderate the building temperature. It does it for free. It does it for 85 years without any degradation in performance. And it's much less expensive than brick and concrete for the same work. In fact, this piece here, which is only about maybe 20 millimeters thick, generally speaking, it simulates about 150 millimeters of brick, which is a brick about that thick. So you can imagine when you build a building, your actual internal volume of your building is much greater. If you were trying to use brick as an internal thermal mass versus phase change, you get a much bigger building on the inside for the same amount of material. It's much less expensive to build and it behaves itself. It doesn't overheat and doesn't underheat. So to learn more about phase change material, there are some other videos online. You can read all of the literature about it. The concept has been around for more than 30 years, phase change. Just not being able to buy it in a packet like this was the problem. Now that you can buy it, you can order online or you can give us a call. We can tell you how much you might need. Typically we recommend about 1 kilogram per cubic metre of air, up to 2 kilograms per cubic metre of air. So it comes in different sheets, all the way from 1.5 kilos per square metre up to 10 kilos per square metre. and you can decide how many square metres suits your building application as a general rule of thumb on that 1 kilo to 2 kilos per cubic metre of air, or you can do a more detailed calculation using software. So if you need help with it, let us know, and that's all from me for now. Thank you.